In the name of God, we have seen that from our previous session that the mean free path can be written as follows. Let me rewrite this. Lambda is the mean free path, is 1 divided by square root of 2 times number density times cross section. Today I would like to focus on sigma, the cross section. What does it really mean? And so we have the topic for today. Collision cross section. Would really want to have a feeling of what that means. Okay, what does sigma really mean? What does collisional cross-section mean? And as usual for this set of lectures, we're going to explain this in a classical way. There are deep things, deep physics can be connected to cross-section, especially when quantum mechanics is also taken into consideration, or when it is addressed or considered or studied at the quantum mechanical level. But yeah, we'll move on classically. So we're going to consider two molecules as usual. Let's say we consider a molecule with radius A1. Let's see if I can sketch something. So let's say this is a molecule with radius A1, and there is another molecule. It doesn't have to be of the same size. Okay, let's say this molecule has radius A2, and we can consider sort of separation, the separation between these two molecules, the distance between them. Let's say it's called big R. So from the center of molecule A1 to center of molecule A2, we have the separation R. Okay, and we consider these molecules as some sort of hard spheres. Let's say spheres of balls, and so one can consider that these molecules or these hard spheres are separated by some potential energy. Okay, so we're going to consider a hard sphere potential energy. Let's call that potential energy to be V. It's going to be a function of R, and this potential energy is equal to 0 if the separation between the two molecules is greater than the sum of the radii of the molecules. So if R is greater than A1 plus A2, V is going to be 0. Otherwise, it's going to be something huge. Let's say it's infinite. If the separation between them is less than or equal to a plus 1. Actually, the separation between the two molecules cannot be less than a plus 1, right? Because you consider when one can reduce R as it is shown in this picture. So remember, R is the separation between the center of molecule A1 to center of molecule A2, and we can reduce R to the minimal possible value. The minimal value which R can take is actually A1 plus A2, because we're considering the molecules to be hard spheres. It means, we cannot break or smash molecule A1 into molecule A2, right? And that's the meaning of this hard sphere potential. Actually, we can draw this potential energy somehow pictorially again, so we can represent VR by this vertical axis, let's say, and a horizontal axis to represent, let's say, R. Well, in theory, in principle, we can think of R to vary from 0, but as I have mentioned, actually R cannot be 0. Actually, R cannot take a value which is less than A1 plus A2, because we are assuming again that the molecules are hard spheres. Okay. So the minimal value of R is actually A plus 1. So at A plus 1, the two molecules experience some sort of potential energy which prevents them from moving into each other, right? So when they are at contact, an energy is a huge energy is experienced. So maybe I can draw that with a green vertical line. So it's going up, saying that, let's say this is going, it's really huge, taking infinite values. So the energy is really infinity. But when R is greater than A1 plus A2, then there isn't any potential energy between the two balls, and then we have here the green line showing that V is 0. So approximately, sorry, my sketch is that way. It should be, the green line should really lie flat on the R axis, the horizontal axis. Okay, so at R equal to A1 plus A2, VR is going to be infinity. To the right of this point, A1 plus A2, V is going to be equal to 0. So here we have V0, here we have, let's say, V is infinity. So this is pictorially what's happening, right? Now, if we consider a collision between molecule A1 and A2, there is a way of quantifying when a collision is going to happen and when a collision is not going to happen. The parameter for quantifying that is called impact parameter. So let's define that impact parameter. Let's say it is letter B. This is actually the closest distance. So this is distance of closest approach if the molecular trajectory, if the molecular trajectories were undeflected. So let's say its trajectories were undeflected. Okay, so that's definition of B. To make it clearer, let's consider another sketch. Let's say this is a molecule, and the center is somewhat here, and then there is, let's say, another molecule with center here, and let's consider that this first molecule is moving with some speed v, and then it gets scattered. Okay, so what does scattering means? It means there is a change of direction somehow of molecule. Let's say this is molecule A1 and this is molecule A2. Okay. So this direction means there is some sort of deflection. Trajectory of molecule A1 gets deflected due to scattering. So scattering is collision. Let's say collision happens, so there is a scatter. A1 gets scattered by A2. So if there were no deflection, what's going to happen? We can sketch that. So the initial direction of A1, let's say this is really horizontal, then it continues that way to be horizontal, right? If there isn't any deflection, we can picture that A1 is going to move in a straight line undeflected, right? And if we draw another line parallel to this trajectory of A1, which is undeflected, and going through the center of molecule A2, then the distance between these two parallel lines is the impact parameter, which is called B. Okay, I hope this is now clear. So if there were no scattering, A would move straight on a straight line, and the closest distance between the centers of the two molecules is going to be the impact parameter B. In this way, we can imagine that actually molecule A1 sweeps a tube, so a volume with cross-sectional area and the cross-sectional area is going to be equal to okay, I'm going to explain this. It's going to be equal to pi d squared. D is diameter, sort of, and the diameter of the tube, pi r squared, sorry, is the radius. Pi r squared, r is the radius of the tube, and the radius is going to be A1 plus A2. So A1 plus A2 is r, so the area is pi r squared. So pi times, in bracket, A1 plus A2 squared. Okay, and actually this is the meaning of sigma, the cross section. So it's like the cross sectional area. this tube, maybe we should sketch it. Molecule 1 is going to sweep that volume. It's going to sweep a tube with cross-sectional area, which is equal to pi A1 plus A2 squared, sort of as its own personal space. Okay, it is on personal space, the tube, and as the molecule A1 is moving, if any other molecule is found within this personal space, within this tube, then a collision is going to happen, right? And this is better seen, let's say, by sketching. Let me sketch something here. Let's say, so we have A1 again. So this is molecule A1 with radius. Yeah, so let me try it this way. Radius A1. And as it moves, it's going to kind of make, let's say, some imaginary tube. Yeah. And this tube, we're considering that it's going to have some cross-sectional area. The cross-sectional area of the tube, sorry, my drawing is somehow, let's try that again. It's a cross-sectional area of the tube. Yeah. This cross-sectional area is what we call sigma, and it's equal to kind of pi into A1 plus A2 squared. Okay. A2 is, let's say, it's the radius of a second molecule. Okay, the molecules could be of the same type, they could be different. We make it general, so let's consider that there is another molecule with radius A2, right? So if I consider the center of this second molecule to be here, right, then one can draw, let's say, another molecule this way. Okay. Okay. But for now, forget about molecule A2 drawn like in red. We can consider some other molecules. So A1, as it is moving, because there are other molecules, let's say with radius A2, then A1 is going to have a personal space, which is this tube. And if any other molecule is found whose center lies inside this tube, then then A1 is going to collide with that other molecule. For example, if I sketch another molecule, let's say this is another molecule in green, and the center of that molecule in green is really inside the tube. So let's say this is molecule B, right? And let's consider another molecule this time around. Let me use black. Let's say the center of this other molecule is outside the personal space of molecule A1. So let's say this is molecule C, and maybe I can call the molecule A2 in red to be molecule A. Okay, so let's say this again. A1 has personal space if any other molecule has its center inside the personal space of molecule A1, then collision is going to happen. That way you can see, hopefully we can see that, for example, what I have sketched here, no collision is going to happen between molecule A, between molecule A1 and molecule C. Okay, because the center of molecule C is really outside the personal space of molecule A, so they are not going to collide. Okay, but there's going to be collisions. A1 can collide or will collide with B, because molecule B has its center inside the personal space inside this tube, the personal space of molecule A1. The same thing with molecule A. The center is just on the surface of the personal space of molecule A1, so they're going to touch. There's going to be some sort of overlap, some sort of collision. So I'm going to add here and molecule A, right? So that's the meaning actually of cross-section, collisional cross-section, sort of. One can consider sigma to be pi times A1 plus A2 squared. The reason just explained, I hope it's going to make sense to you. Okay, so we can see that the bigger this cross-section sigma is, the more probable it is for molecule A1 to get collided with some other molecules, okay, that happens to have their center inside its personal space. Okay, so all this is classical, and it helps somehow to have a picture of really what that means. But note that there is going to be a note here. Note cross sections in nuclear and particle physics can be much larger than the size of the particles. Okay, because there are, because of strong interactions, can happen. Strong interactions can happen at long distances between the molecules or between the particles are. That is actually V is not equal to 0. Let's say at are much larger than A1 plus A2. So if you remember this picture, this sketch, whenever R is bigger than A1 plus A2, so in this region, the potential energy for the interaction between molecule A1 and A2 is 0, meaning that there isn't any interaction between A1 and A2, right? Because they are separated between each other. But at the point R equal to A1 plus A2, there is this huge potential energy experienced by both molecules. For the case of nuclear and particle physics, actually V is not equal to 0 in this region, and for that reason the cross-sectional area for the interactions, for nuclear and particle physics interactions, can be really much bigger than the size or the cross-sectional area of the molecules under consideration, right? Because pi r squared is sort of a measure of the size of the molecules. I think that's it for today. Some gists about cross-section, and catch you next time. Goodbye for now.